So we will start with stationary Gaussian process or stationarity. So can you guys guess what stationarity is all about?
Distribution function will not change if we change the epoch with certain time.
So the general definition is this. So let's say I'll just I'll write a diagram. So essentially, if you look at a stochastic process x of t, okay, this is a stochastic process, and then you take any, let's say, k random variables or k in n, okay, fix this, and then correspondingly choose k time instances. Okay, let me call that as t1, t2, etc., tk. Okay, so these are the k time instances at which you are going to look at the random process. Basically, you look at x of t1, x of t2, okay, and so on. You look at x of tk. So you'll get the corresponding k random variables or a random vector. Now you look at the joint distribution of this. For example, I'll write it as f of. I'll look at it in terms of the CDF. So if f of x of t1, x of t2, etc., x of tk, right, of some x1, x2, x3. So this will tell me the joint distribution of these k random variables. Is that clear? Fine.
Yes, sir.
Okay. Now, if this is same as the joint CDF of series of or sequence of random variables with some delay, let me write that as follows. So this is f of x of t1. I'll delay it by tau. Okay. X of t2. I'll delay it by tau, and so on. X of tk delayed by tau. So of x1, x2, xk. So if the distributions match, regardless of what, for any tau you pick, the delay. Okay. So if I want to write it pictorially, so suppose I have picked these 3 points. Okay, t1, t2, t3. Okay, I'm looking at Gauss, random process at these times. Now, if you look at the joint distribution, it will be same as the joint distribution. For example, if you delay it by tau. Okay, you look at these 3, or if you delay it by a little, for example, something like this, right? So it doesn't matter how much you delay. So the distributions match. Then we say that the stochastic process or the random process is stationary. Is that fine?
Yes,
Is
sir.
that
It is
fine?
something like, sir, invariance under scaling, no, sir.
Hmm?
It
Not
is something.
scaling, right? It's a delay.
It's
You
Shifting.
are shift in time. Yeah,
yes.
you are sampling at, let's say, a certain time instances. You look at the joint distribution, shifted by tau. You look at the joint distribution, they will match regardless of the amount of shift. Okay, so formally, this is how do you define this? We say that x of t, this is your stochastic process, right? Let's say t belonging to t is a stationary, I'll say is stationary, or is said to be stationary if you take any k, right? If for any k in n, for any t1, t2, etc., tk in the set t, for any tau belonging to R, the following holds, right? So what is that? This is f of x of t1 till x of tk of x1 through xk is same as f of x of t1 plus tau x of tk plus tau of x1 through xk. Is this fine? Any questions?
No, sir.
Hmm? This is fine, right?
Yes, sir.
Now, the question is, how does this translate to, for example, a Gaussian process? What do you mean by if I say a Gaussian process is stationary, or if I consider a stationary Gaussian process, what is it that I need? Okay, so if the distributions match, the corresponding moments also should match, right? For example, if you look at the means should match. Do you agree? The second moment should match, the covariance should match, everything should match. Do you agree?
Yes, sir.
What do you mean by that? So what is the implication? Let's look at the first implication of this. If you look at expected value of x of t, right, this should be same regardless of what t is, because this is same as expected value of x of t plus tau for all tau. Do you agree? And t. This is what the stationarity says, because the distributions are same, therefore the expected value should be same. So this implies what? Expected value of x of t, I'll take tau to be minus t. So this is same as expected value of x of 0. Let me call it as mu. Okay, so the means, it doesn't matter now. So the mean wouldn't change across time. So you take samples at any time instance, the corresponding random variable will have the same mean. Okay. So what is the second implication? So suppose I take the covariance. So what is covariance? So suppose I take, for example, expected value of x of t1, or let's call it as x of t, minus the mean is the same, times x of tau minus the mean. Mean is same, right? So this is the covariance evaluated at time t and tau, right? So now what will happen to this? What can you say about this? Any idea? What will happen to the covariance? Hmm? I'll, for shorthand, I'll write this as some k of, it depends on two, right? K and t and tau. Okay. Now what I can do is I can shift. So k of t comma tau, this is same as k of t plus t1, or I'll write some L, okay, L, and tau plus L. Do you agree? If I shift the whole process by L, things shouldn't change. Do you agree?
Yes, sir.
Right?
If it is
So
stationary,
this
then
is true for any L that I pick, right? So that means k of t comma tau is equal to k of t plus L comma tau plus L regardless of what L is. So what I will do is I'll pick L to be equal to minus t. Okay, choosing L to be minus t. What do we get? K of t comma tau is k of 0 comma, so tau minus t, right? So this is true for any t and tau, right? So that means if you look at the covariance k of t comma tau, it depends only on the difference. Do you agree? Is this clear? K of t comma tau depends on the difference. Any questions? Jayan, Praveen, Ayush, Sumit. Hello. You guys can hear me?
yes, please.